All right, so welcome back, guys. Today we're going to talk about Newton's laws of motion. Isaac Newton's this guy who lived in the 17th and 18th century, and he did a lot of work. He first postulated the idea of gravity. He said, legend has it that he saw an apple fall out of a tree, and because of that, he started to come up with these postulates, which eventually grew into theories and eventually laws. He said that there had to be a reason for something like this to happen, for the apple to keep falling. So in this process, he became known as the father of modern calculus. So what that really means is he started using calculus for the first time. And you guys, only a couple of you are in calculus, but we don't really go into the full scope of what calculus can do in physics. It's a very powerful tool. We only do algebra-based physics. That's okay. So Isaac Newton, father of modern calculus, very smart guy. He came up with these laws of motion. Newton's first law is also called the law of inertia. It says that an object is going to try and maintain its state of motion. So if it's moving, it wants to maintain that state of motion. If it's sitting still, it wants to sit still. So the only way it's going to change from those states is if something else acts on it. Let's see here. So in the absence of friction, an object is going to stay in motion. So friction would represent an unbalanced force. So if I've got a car moving down the road, we know that it's not going to stay in motion unless I hold the gas down. If I were to just punch it and let off the gas, then I would eventually slow to a stop. And what slows me to a stop is the friction. So it could be the air resistance, which is air friction, and it could be the friction of the tires on the road, and there's all kinds of stuff that slow us down. Friction is always going to be our unbalanced force, if nothing else is acting on it. There are two parts to Newton's first law. It says that one that predicts stationary behavior and the other that predicts behavior of moving objects. Let's see. What we have here, we have ourselves a little flow chart. So if we have an object at rest, then its velocity is 0, and it's going to maintain that 0 velocity if no other force acts on it. We see here we have a 0 acceleration, and so we're going to stay at rest. If we're in motion, our velocity equals something other than 0 meters per second, and we still have 0 acceleration. Because we have 0 acceleration, we're going to maintain our current state of motion. So if we're moving in a straight line, we're going to keep moving in a straight line. We can say that objects are going to keep doing what they're doing. So inertia can be thought of like the laziness of an object. So if I'm at home on my day off, most of the time I want to be lazy. I want to sit on the couch, and I want to keep sitting on the couch. So inertia is very similar to that. If the object is in motion, then it's going to want to keep in motion. If it's sitting still, it's going to want to stay still. And that's just how I've called it. This gives us a brief description of it. And this guy thinks, objects are going to keep doing what they're doing. So it's a natural tendency of objects to resist a change in their state of motion. So it's naturally, I'm going to resist changing getting up off the couch. Very similar. The tendency for an object to resist that change is called its inertia, which is the resistance that an object has to a change in its state of motion. So the word inert means not living or not doing anything. So inertia is this quantity that tells us how hard it's going to be to change the state of motion of an object. So our elephant here, it's going to be hard to push him. He's huge, so he has a huge inertia. Because he's so big, he's going to resist any change in his motion. And once he gets moving, it's going to be really hard to get him to stop because he's got inertia. You can also think of the same thing like a train. Elephant is at rest, and he's going to want to stay at rest. It's going to be very hard for us to get him out of that rest state. You've probably seen this before. What we have here is a tablecloth. You see the guy yank the tablecloth out from underneath the table, and all the dishes stay standing. This is because of inertia. These dishes and the candle, they don't want to get out of their state of motion. Their state of motion is rest, and we yank the tablecloth out from underneath, and they're going to stay where they are. So we're going to overcome the inertia of the tableware, if that makes any sense. We've got another couple of applications to this. So think about your car. So as you're in your car and you come to an abrupt stop, you're pulled forward in your seat. So because you have mass, you are pulled forward. Your car slows down, you're not a part of your car, so you want to keep moving forward while your car slows down, and you get caught by the seat belt. If you're not wearing that, you might get caught by the steering wheel or the airbag if you get into an accident. So we got a little animation here. So if our car is to abruptly stop and the seat belts aren't worn, our passenger is going to go flying head over heels out of the car. He wants to maintain that state of forward motion. So because he's moving with the car, he has the car's same velocity. He wants to keep that velocity. Got another one up here. Also, make sure you wear your seatbelt. Your seatbelt is designed to counteract gravity. I'm sorry, not gravity, inertia. Got another one here. We've got a truck with a ladder on the top. So this truck, or you can consider it a log truck. That's one reason I don't like driving by log trucks on the road. They're moving really fast, so those logs are moving really fast. If the truck were to hit me, then those logs are going to go up through the front of the cab. So if you look at our ladder here, our ladder leaves the top of the truck and keeps moving in its forward state of motion. And we got another one, motorcycle. We're going to stop. We've got a rider on the motorcycle. He's going to want to keep going the same speed as that motorcycle. So if he's going 70 and he runs into a wall, he's going to keep going 70, and the motorcycle is not. All right, so mass, very important quantity. Mass is what makes up inertia. So inertia is only dependent on mass. So depending on how big something is, it's going to be more resistant. So the heavier something is, the more stuff is in an object, like my elephant, it's very massive. So because it's so massive, it has a great inertia. It resists change in its motion a lot. A feather doesn't have a great mass, so it's very easy to change the motion of a feather. So the measure of inertia that we use is mass. Mass is measured in kilograms, kg. Contrary to mass, we have weight. It's not necessarily contrary, but in addition to. Weight is the vector of mass. So since mass is a scalar, we can't have negative mass. We need to assign a direction. And weight is how gravity influences our mass. Gravity is a vector, therefore, since gravity is a vector and mass is not a vector, anytime you multiply the two, then you get a vector sum, so it has direction. So your weight is due to the influence of gravity, so it's going to be straight down to the center of the earth. Your mass doesn't change no matter where you go, but if you were to go to the moon, you'd be able to jump higher because gravity doesn't influence you as much because the moon has much less mass than the Earth does. But your mass will stay the same. So your mass stays the same, and therefore your inertia stays the same. So if I have an elephant on the moon and I go to the moon, it's still going to be as resistant to a change in motion because its inertia hasn't changed because its mass hasn't changed. But anyway, so we figure out weight, the weight of a body is the force that pulls it downward because of gravity. In order for us to solve for weight is a force, we use this equation. Force of gravity, so our weight, equals our mass times gravity. And the units for force are newtons. We've talked about newtons briefly. But to figure this out, so I'd put my mass, which is about 75 kilograms, and I'd multiply it by gravity, which is 9.8 meters per second squared. So 75 kilograms times roughly 10, 9.8, would be about 750 newtons. So my weight is 750 newtons. Pounds are a measure of weight, so it's the American measure of weight. But newtons are the international, and it's really used only in scientific communities. And if you go into like different countries, they use kilograms as their unit of weight, but we know that that's a unit of mass, so we'll no longer do that. So to solve, we know gravity is 9.8 meters per second squared. We know that. So to solve, we want to figure out the weight of 6 kilograms of potatoes. So the first thing that we do is we write down what we're given. We're given a mass of 6 kilograms, and gravity is 9.8 meters per second squared. So our weight is mass times gravity. So our mass is 6, gravity is 9.8. We multiply them together, and we get 58.8 newtons. Fairly simple. So now let's just say we want to go the other way. We want to figure out the mass of 6 newtons of potatoes. So let's go the other way. So we write down what we're given. We're given a force of gravity. We're given a weight, 6 newtons. And we're given we know gravity, 9.8 meters per second squared. And our force of gravity is mass times gravity. We do the algebra. We rearrange. So we divide, and we end up getting mass is our force of gravity. over gravity, the constant. So it ends up being 6 over 9.8, so less than 1, so 0.61 kilograms. So 1 Newton is about 4.4 pounds. So if you multiply this by, I'm sorry, if we had this in pounds, we would be able to figure that out that way. And so what you're going to do, not yet, but when we're done with the video, is you're going to complete A through H on page 60, and we're going to check these in class. All right, so we got another thing we're going to worry about here. Actually, I'll go back to that. A through H on page 60, just to remind you. The forces on the book are balanced. So we've got a physics book here, and we need to figure out what the sum is. And we've already done this a little bit. We summed our forces. We know that Earth pulls downward on the book, and the book is supported by the table or by whatever it's sitting on, and that's the normal force that we show. Since we're not moving, since we're not accelerating, the downward force of weight and the upward force of the table pushing back are equal to each other. We're going to add them together. So that is our net force. Unbalanced forces occur only when our net forces don't equal 0. If they equal 0, then they're balanced and they cancel each other out. If they're unbalanced, then they equal different things. So if gravity was heavier than the table could push, or your weight is heavier than the table can push back, you're going to go through the table. You're going to break it. That just makes sense. If I sit in a chair, if I'm too fat to sit in a chair, then that supports my weight, then I'm just going to break the chair. I'm going to go through the chair. All right, so this guy, he's standing still, and he's got an upward force through the floor on him, so that's his normal force, and Earth's going to pull him downward. They're balanced. Now we've got a physics book. So now this physics book is in motion. So someone has put a leftward force. Hang on, let me see. All right, so someone has moved the book to the right. Someone's moved the book to the right, and Earth pulls down, table pushes back up, and something about the table has to do with the composition of the table. It provides a leftward force on the physics book. We've talked about this. So we've got this physics book with an unbalanced force, which is friction to the left. So since that force is unbalanced, we're going to change our state of motion from moving at a constant velocity to slowing down because we have this frictional force. And eventually we're going to slow down to a stop. All right, so what we have now is we have a net force, or several different net forces. It's the resultant force. So sigma F, sigma is a Greek letter, equals our resultant force. So if we've got 5 and 5 in one direction, it's going to equal 10 in that direction. We've done this. So this stuff should all be pretty much self-explanatory. Right, so now we're going to have some examples. So the rules can be for adding vectors. We can apply them to our free body diagrams, which we've already started to draw. So we've got these three free body diagrams, and well, let's go ahead and work those out individually. So we've got an upward force, a tension force of 1,200 newtons, and a gravitational force of 800 newtons. Because there's a difference here, our net force is 400 newtons. So we've got our tension force, which is 800, and we've got our gravitational force, which is tension force is 1,200. Our gravitational force is 800 down, so we make that negative. So 1,200 plus negative 800 would give me our sum of our forces, which is 400 newtons. With this one, we've got a 600 newton force of air resistance upward and an 800 newton force of gravity down. They're greater, so let's add them up. We've got our force of gravity plus our force of air. We know that one of those has got to be positive. Let's say that downward is negative. So our force of gravity, we did it the other way around, excuse me. So our force of gravity is 800 newtons, and our force of air resistance is 600 newtons. So our answer is 200 newtons downward. It's in the downward direction. This one, what we have now, we have a normal force of 50 newtons, a gravitational force of 50 newtons, and a leftward force, a force of friction of 20 newtons. So these two forces are in opposite directions, so they cancel. And the only force that we have is this 20 newton force. We show that mathematically by writing it like this. The sum of our forces in the x direction, and the only force in our x direction is our frictional force, right there. That's 20 newtons to the left. All right, so now we're going to have equilibrium. So we're in equilibrium only and only if all of the forces acting on it add up to 0. So we've got the sum of our x forces is 0 and the sum of our y forces is 0.